Now for some analysis on the inclined plane. What are all the forces acting on this cart? You would probably say that there's weight, and that's going straight down. Some kids say that the weight's going down the plane. We're getting ahead of ourselves. Just draw that arrow straight down. There's another force acting on the cart, the spring scale. That's pulling up the plane. Well, there's got to be one more force, because if there was a force this way and a force that way, this cart would be in motion, but it's staying still. We know all the forces add up to zero. Some of the kids in the class suggested that the board is pushing at an angle like this. Well, that is perpendicular to the plane. Let's find out if that's really the case. I'm going to pull the board out from under the cart. Cart really doesn't go very far, does it? The board just moved a whole lot. Here it is again. The cart's not really going anywhere, but the board's moving a lot. That tells me the board can't push parallel to its surface. But if I turn the cart upside down, hey, it's moving with the board. There's a whole bunch of friction here, allowing for a force parallel. But if I have just the wheels, then it doesn't go anywhere because there's no force this way. The force has to be this way, obviously, or the cart would be falling to the floor. So as we tilt the plane, the spring scale is pulling this way, and the plane is pushing this way. This is what we call the normal force. Well, let's draw a diagram of the apparatus. Here's the inclined plane. There's the horizontal, and you should draw these with a ruler. We typically measure the angle from the horizontal. And we have the cart, the spring scale mounted to the block of wood, clamped to, all of this is the apparatus. To draw the free body diagram, I'll get rid of the spring scale, the block of wood, and the clamp, but I'm leaving the inclined plane because we're going to see how important that is. What's the first force vector I should draw on here? How about the weight? And make sure you label it. I'll put in the force of the spring scale. Since you know that the cart is not moving, there must be a third force, so it all cancels out. That's the normal force, the force of the plane pushing on the cart. And it has to push perpendicular to its surface, as we just saw in the demonstration. These diagrams must be drawn carefully. The force of the spring scale is parallel to the plane. The normal force is perpendicular to the plane, and we can check by using a sheet of paper and just putting it up here and saying, hey, yeah, we're pretty close. So even if you don't have a protractor, you can still check your work. To further the analysis, we would like to draw the X and Y coordinates. Imagine the plane is not there. This is starting to look like a force board lab, or a hammock lab, or a truss lab. It's all the same stuff. You have an object at rest, and all three forces have to add up to zero. But there's something that we can do in this case that we didn't do before. You take a look at that weight vector. It's right on the y-axis, and we like that. We don't have to break it up into components. But I have two vectors here now that I have to break up into components. Well, what's better than putting one vector on the axis? How about putting two vectors on the axis? Let's tilt the X and Y coordinates. Now I have an Fn on the Y and the Fs on the X. That works because they're right angles to each other. It's going to make the job easier. We only have to break up the weight vector now instead of two other vectors. Well, what's this angle in here? Well, let's see. If that was 30 degrees, then the angle here would be 60. That would make that angle 30, because this is a right angle to this. So if that's 30, that's 60, that's 30, theta can go there as well. Now we can break up the weight vector into X and Y components. This one is the Y component, and that's the X component. They're at right angles to each other. Now, I know this whole thing seems a little weird because it's on a tilt, but you can hold the paper any way you want to, tilt your head, and get used to the idea, because it's much easier to do inclined plane problems when one of the axes is parallel and one of is perpendicular to the plane. I like to call this component The component of the weight that is perpendicular to the plane. I like to call this component the component of the weight that's parallel to the plane. Now, if you know a little trigonometry, you can figure out the formulas for these guys. This is the adjacent side of a right triangle. So this component is the weight times cosine theta. This component is the weight times sine theta. Now we know that this cart is being held stationary. It does not roll down the hill. This component is what's making it roll down the hill. What's stopping it from rolling down the hill? The spring scale. So how big does that spring scale have to pull compared to the weight going down the plane? Well, of course, they have to be equal. So the force of the spring scale is equal to Fw times sine theta. Now we know this cart does not fall through the plane. Fn is stopping it from falling through the plane. How big is Fn? It has to be equal to this component of the weight, which is Fw times cosine theta. Well, in this lab, you had to make a graph of the force of the scale versus theta. Make sure you label each axis and put down the units. When you make your graph, use a ruler to lay it out and do it on graph paper and make sure these numbers are spread out so you fill up most of the paper. No need to put tenths of a Newton along here. You can space it out like this, just a few numbers. You'll be on graph paper, so you'll be able to read it. At first, you graph the experimental data. And you were supposed to draw a smooth, best fit curve through that data. You never want to connect all the dots with a squiggly, wavy line. That's just plotting your error. What you want to do is average out your error by having some dots high, some dots low. You pick the middle of the road, and that's a way of graphically averaging out your error. And we make sure that we label that this red line is the experimental. We'll use blue for the theoretical. How are we going to do that? Well, we have a formula here. Fw sine theta is the force of the spring scale. That's a theoretical formula. If you do it right, it should really line up along a very nice curve. Drawing these best fit curves is a bit of an art form. You just don't want to have a lot of bumps and waves to them. So you practice that. Now, do you think 0, 0 should be on this graph? Yeah, of course. If this thing was on the ground, then the spring scale would read 0. There would be no need for it to pull. Most of the kids had data that matched up quite nicely. So the question became, what is the name of this kind of curve? Oh, some kids said it's some kind of exponential, logarithmic. I heard parabola, half a parabola. You know what it is? It's a sine curve. It's a sine curve because that's the function that we just graphed. We derived the formula using this diagram. That's the name of this curve. But most kids know a sine graph is something that goes up and then down. And well, hey, it's only one portion of a sine graph. It only goes up to 90 degrees. Well, you might be wondering how I actually made this graph because I didn't tell you what Fw was. Let's look at the graph and see if we can figure it out. Well, at 90 degrees, we are straight up. Well, that means the spring scale is holding up the whole thing. So what is the weight of our cart? You go up here, you'll go over here, and you say, oh, it's just about 4 newtons. This weight is what you get in the lab during the experiment. You weigh the cart with whatever you have in there. Once you have that value for the weight, you can use this formula to make your theoretical graph. Now we're going to make a graph of the normal force versus the angle. That's going to be done theoretically. At 0 degrees, we plug in the weight, and we're going to find out the normal force is equal to the weight. That makes sense by looking at the diagram. If this thing was flat, the board would have to hold up everything. If we keep increasing the angle, we can keep plotting the normal force, and we see a graph that curves down. When the board is tilted all the way up, there won't be a normal force. So when the angle is 0, we're not going to have any force of the spring scale. There won't be anything necessary to pull it sideways. We have the weight going down and the normal force holding it up. These two forces are equal. So we'd say the normal force is equal to the weight, and the force of the scale pulling is 0. And that's for the angle equaling 0 degrees. And what about 90 degrees? The weight is still pulling straight down, and it will be the spring scale that keeps it from falling. So it's equal to the weight. The normal force is 0 now because there's no need to stop it from moving sideways. Well, that information all agrees with the formula and the graph. Well, you don't have to believe my diagrams. You've got the equipment. You can try it. Hold this thing vertically. And look, you don't even need the board. So there's no normal force. Okay, just a word about how to measure the angle. You have to find the little tiny hole at the center of your protractor. And then you want to put the protractor flat on the table, move it back and forth until that hole touches the bottom of the ramp. And then you measure your angle from the horizontal up to that point. This is about 28 degrees. Some kids measure to the top of the ramp, but that doesn't make any sense because the pivot is on the bottom here, and that's where I'm putting the hole. If I was going to measure to the top of the ramp, I'd have to put the hole on the top of the ramp. Here's a diagram of what I'm talking about. You want to measure this angle. So you put your protractor center right here. And then you read to the bottom of the ramp. But some protractors have the center above the bottom of the protractor, and you can't get that dot right at the corner. So you just slide your protractor over where the dot touches the bottom of the ramp, and then you measure the angle from 0 up to the ramp. It doesn't matter that the line is higher or lower. As long as the bottom of the protractor is horizontal, you're going to get the right angle. The mistake kids make with their angle is sometimes they measure from 0 to the top of the ramp while the center of the protractor is on the bottom of the ramp. That's not going to work. You can see that's just wrong. Well, you can avoid all your protractor error by using the meter stick. You can just measure some arbitrary length and then a height up to the bottom of the ramp. Inverse tangent, you got your angle. This is actually more accurate than using the protractor. To test our theory on the normal force, you could get a second spring scale and get a loop of string and rig it up like this. Now I'm pulling perpendicular to the surface of the inclined plane. As soon as I pull hard enough just to lift it off, I can look at the spring scale and get a reading. Instead of the plane pushing with a normal force, I'm just going to pull with another spring force, and it should be the same. And now you can see that this is just like the Hannock lab with two different angles. One's going this way, one's going this way, and the weight's going down when I lift this thing off the plane. So on a quiz, I'll give you an inclined plane, put a little card on there, and ask you to draw the force vectors acting on the cart. Well, what could go wrong? For some reason, I've seen kids draw the weight vector like this. I guess they know the weight goes down when the ramp is flat, and when the ramp tilts, the weight vector tilts. Doesn't work that way on planet Earth. Kids love to draw the weight all the way down to the horizontal line. It doesn't have to be there. It all depends on the scale you want to use. Then I tell them to break up the weight vector into components that are parallel and perpendicular to the plane. And this is what I get. Well, that makes no sense at all. These components can't be bigger than the weight that causes them. That perpendicular component is going to have to stop right about here. The parallel component would have to stop here. Because if I put them tip to tail, the perpendicular and the parallel have to get me to the tip of the weight vector. Don't forget, they're perpendicular to each other. One's parallel to the plane, one's perpendicular. Then I have kids drawing the normal force straight up. Remember, it's a normal force, and that means normal to the surface. So it's got to go just like that. Now, how long should it be? As long as this perpendicular component is, because that cart did not fall through or lift off the plane. Well, most kids are pretty good at drawing in the spring scale force. It's parallel to the plane. But what's wrong with this diagram? That's way too big compared to that parallel component. They have to be equal. Now, that's a little bit better. Don't forget to label the angle. Just one more demonstration on the angle. You could picture if I put a piece of paper here and I rotate it up into that position. I rotated the paper through this angle. But I also rotated this edge through the same angle. So this vector over here would have rotated around the same amount that I rotate this, because they're perpendicular to each other. And let's finish off with a tip-to-tail diagram. We start with the weight vector. Now I'm going to add the spring scale force and finish by drawing in the normal force back to the origin. That shows that all three forces add up to 0. Don't forget, it's a right triangle, and the angle is up here. So why do we need to know about inclined planes? How about cars braking? People skiing down a mountain? Or maybe me riding my bicycle up a mountain in Wyoming? All involves inclined planes. We'll see problems like these later.